进行直播。OK， 好了。好，谢谢。然后你把那个 link 看我再传一次。Okay. Hello. Okay, let's start. Okay, first question. What is kernel trick? So for support vector machine, we could sort of project the features from the original dimension to a high dimensional space. But we know that it would be computationally costly or even infeasible to project the features to high dimensional space because they could be infinite dimensional. And so instead of explicitly mapping the features to high dimensional space, we have some way to compute the inner product in the original feature space. And then after that, we have some extra computations, and the result is equivalent to mapping features to high dimensional space and computing the inner product in the high dimensional space. Okay, so that's kernel trick. Essentially, you have some you use some simpler computations to sort of achieve the same result. Okay, next question. For SVM, if we increase the margin from very tiny to a moderate size, then the first question is the training error tends to increase or decrease? The answer should be the training error tends to increase. Okay, the reason is that, okay, let me give you a visualization. So suppose we have some, let me open the pencil. Okay, suppose we have some positive instances here, we have some negative instances here, and of course we have infinite ways to separate these positives and negatives using a single line. So one choice is if if this is the discrimination function, then in this case the margin would be roughly this large, right? And then if we increase the margin a little bit, like to maybe here, then of course the training error will increase. You make more error on the training data. Okay. But for the test data, usually they would decrease because you're sort of more robust to the outliers. Next question, what is the difference between a linear SVM and logistic regression? So first, there are differences only in the loss function. Okay, for linear SVM, that means we don't project the features into high dimensional space. Okay, so that's basically you use the original feature space and you perform the you sort of assign the hinge loss. So that's essentially just a different loss function. And for logistic regression, the loss function is simply the logistic loss. Okay, so they are quite similar. Next question, what is the difference between a linear SVM and an SVM with a linear kernel? The answer is, if we just talk about the prediction power, then essentially linear SVM and SVM with linear kernel, they are identical. If we are just talk about their predicting power. But they are different only in the sense that when we say linear SVM, usually we use the original, we sort of, just like logistic regression, we try to find the W's or thetas directly. So at the predicting phase, we essentially still compute something like, we still use a linear combination of the feature and the parameters. It's essentially the inner product of the features and the parameters, and we use that for prediction. But for SVM with linear kernel, we compute. We still compute the inner product between a training instance and the target. We still do that. Okay, so in other words, so when we say use kernel trick, remember that we need to perform some kind of product. Right, so for SVM with linear kernel, although its predictive power is the same as linear SVM, but we sort of using a different way to solve it. But their models, in terms of predictive power, they are identical. Okay, next question. Compare SVM with polynomial kernel and linear model using polynomial two-feature engineering. What are their advantages and disadvantages? Also here, I have to be more specific. So for polynomial kernel, I mean with degree 2, which means that the kernel is something like x, t, and xi plus c and square, something like this. Okay, what's the difference? Compare SVM with polynomial kernel and linear model using polynomial two-feature engineering. So again, they are equivalent in terms of predictive power. But when to use which? Okay, so then that could be depends on the characteristics of your feature. If your feature has a lot of zeros, then perhaps using the polynomial two-feature engineering, that could be more efficient in terms of training and testing. The reason is that when you create these polynomial two features, if you have a lot of features whose values are zeros, then multiplying 0 by anything, they would still be 0. So that's why in terms of training or testing, this would be more computationally more efficient. But on the other hand, if your feature is, if there's no zeros in your feature, then perhaps using polynomial kernel would be more efficient. Okay, so we spent I think at least 2 weeks to talk about SVM. So let me sort of quickly review the entire roadmap about how we derive the SVM in case you forget it. So in the beginning, we said that we want to maximize the margin under some inequality constraints. Right? We want to maximize the margin or minimize the inverse of the margin. And for the inequality constraints, we want that W transpose X plus B multiplied by, let's say this is the ith training instance, okay, multiplied by yi to be larger or equal to 1. That's our constraint. Right, so initially we said that we want to maximize the margin with these inequality constraints. And then this can be solved by a standard QP solver, or after some we also show that you can in fact also solve this using a gradient descent by sort of massaging these formulas a little bit. And then we introduced kernel functions to map the features into high dimensional space, and that could be even infinite dimensional space when we use the RBF kernel. Okay, so you can map the features into infinite dimensional space, and in that case, it's impossible to compute this W directly. Right? If your x becomes phi of x, and that phi of x is infinite dimensional, then it's impossible to find a W whose length is infinite dimensional. So in that case, it's impossible, or it's difficult, or even impossible to solve this problem directly. And then we show that because of the KKT condition, we show that W can be written in another form. And then in that form, sort of essentially that's where the kernel trick comes from. You don't need to really map the features into high dimensional space. You can do some sort of computation in the original dimensional space, and the result is equivalent to computing the inner product in the high dimensional space, or that could be infinite dimensional space. And then we show how to solve and then we show the primal form and dual form, and we show that we could also solve the dual form based on a standard QP solver. Okay, so that's sort of like the entire roadmap. And we got a question asking, so we talked about ROC curve a couple of weeks ago. Remember we said that ROC curve is sort of considering all the possible thresholds in computing the true positive rate and false positive rate and connecting all the dots together. So apparently, if you use area under ROC curve as a measurement, then you need more computationally it's more expensive compared to just report a single accuracy or F1 score or anything, because you need to try different thresholds. So some students said that it seems that to plot the ROC curve it's very expensive. So it's indeed expensive, but it's not as expensive as some students thought. So if we have n test instances, plotting the ROC curve or computing the area under ROC curve requires order n thresholds. And so in fact, you just need to go through all the, I'm sorry, this should be the test instance. Test instance once, okay, then it's order n. So let me give you an example. This is the example we shown a couple of weeks ago. So initially, our threshold is set very high. Then all these instances will be regarded as negative. But from the 10 instances, only 1, 2, 3, 4, 5, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. Only 6 of them are indeed negative. Okay. So your true positive is 0 and your false positive is 0. And then we want to compute true positive rate and false positive rate. And true positive rate is simply TP divided by TP plus FP. Okay, let me remind you again. True positive means that I predict something as positive and I'm correct. That's true positive. And false positive is I predict something as positive but I'm wrong. and that's false positive. Okay, so true positive rate is out of the truly positive instances, how many of them are correctly predicted as positive by my model. So that's true positive rate. So the definition is TP divided by TP plus FP. And the definition of false positive rate is out of the truly negative examples, how many of them are incorrectly predicted by my model. Okay? So in the in the denominator, you should put number of the truly negative examples, which means that should be true negative plus false negative. Out of all the there should be true negative plus let's see, false positive. So in the denominator, that's out of all the truly negative examples, how many of them are incorrectly predicted by my model? So in the numerator, there should be false negatives. I predict negative, but I'm wrong. Okay. And is it correct? Let me think about it for a moment. Sorry, this should be false positive. Let me think about it for a moment. Am I correct or not? Yeah, it should be false positive. In the numerator, it should be false positive. Okay, so so when the threshold is very high, I predict nothing as positive. So of course, the true positive and false positive are both 0. If I set the threshold a little bit lower here, then all I need to do is check whether this one is correctly predicted or not. If I set the threshold here, that means this one will be predicted as positive, and I'm correct. So true positive will be from 0 to 1, and false positive doesn't change. Okay, and if I move the threshold a little bit lower here, then these two instances will be predicted as positive, and both of them are correct. So the true positive goes from 1 to 2, and your false positive is still 0. And if you continue to lower your threshold here, then these three instances will be predicted as positive. And in this case, your true positive is still 2, and your false positive goes from 0 to 1. Okay, so your true TP becomes 2, and your FP becomes 1. So all you need to do is you just keep track of TP and FP. If I continue to lower the threshold, this one is incorrectly predicted, so FP continue to +1. And further here, this one is successfully predicted, so your TP +1, and so on. So after all this, you eventually get, you have 4 true positives and 6 false positives. Because in here, we have only 10 instances. And if your threshold is very low, of course, you will predict everything as positive. So they will either be true positive or false positive. Okay, so the summation of these two has to be 10 in this case. And then all you need to do is, we said that this is the relationship between TPR and FPR. And we have 4 positives in this case. So it's sort of like we have 4 positive cases. So whenever you have one extra true positive, the true positive rate increases by a quarter. Okay, so you just need to have 1/4, 2/4, 3/4, and 1 here. And for the false positive rate, because we have 6 negatives, so whenever you have one extra false positive, the false positive rate will be increased by 1/6. So we have 1, 2, 3, 4, 5, 6. So that's 1/6, 2/6, up to 6/6, which is 1. Okay, so that means initially you are at 0, 0. And then you just look from the top to bottom. When you see a 1, you basically just move upward. When you see another 1, you move upward. When you see a 0, you move rightward. You see another 0, you move rightward. You see another 1, you move upward. And another 2 zeros, so you move rightward and rightward. You see a 1, you move upward. You see another 2 zeros, you move rightward and rightward. And that's the ROC curve. Okay, so of course it's computationally more expensive compared to, for example, accuracy, single score, because you need to compute several different scores. But it's not that bad. It's just order n. Okay, if you have n instances, you just compute it like this. So in fact, if you think about it, if you really want to report, let's say, accuracy of the test data, you still need to look through all the instances once, right? So in terms of time complexity, they are identical. To get the accuracy of the test instance, if the test instance has n samples, you still need to look through all of them once. So that in terms of time complexity, they are identical. It's still order n. All right, so that's a response to the ROC curve. Oh, and the other question is, after you report, for example, the area under ROC curve, but in practice, you still need to decide a threshold somewhere in the future, so that at the prediction phase, you still need to decide a threshold to say this instance is positive or this instance is negative. Then how to decide this threshold? Okay, so in this case, that really depends on your task. If you really care about precision, if that's your use case, then you should set the threshold higher. If your target towards the recall, then you should set the threshold lower. So that really depends on your need. Or another way to do it is, if you really don't know what to do, if you really just want a reference point and you are not sure whether you want a high precision or high recall or whichever, then another way people sometimes use is find a point. Find a point that is closest to this 0, 1 point. So that is this point here. This is the point that is closest to this 0, 1. And then just use this place as the threshold. The place where your true positive rate is 0.8 something, and your false positive rate is roughly close to 0.2. Okay, so that means you just trying to find a line whose slope is 45 degrees, and that's a tangent line to this ROC curve. And this could be one way to find the threshold. Okay. Or you could define or determine the threshold based on your task. So for example, if you want to diagnose a rare disease, and you believe that recall is very important, you really don't want to miss any patient, then in this case, you should set your threshold lower so you could find most of the patients, even though in this case, you might sort of misidentify some healthy people as sick, but that's probably okay in this case. On the other hand, this is a case where you probably want a high precision. Okay, so imagine that you are building a framework to detect the bot for a game company. You want to identify which users, which players are not real human. And then in this case, if you identify a real user as a bot, he or she might be very angry. You really don't want to do that. On the other hand, if you misclassify a bot as a normal user, of course that's not good, but that's probably not that bad. Okay, so in that case, you really want high precision. When you say someone is a bot, you better be sure about it. So in that case, you probably want to make your threshold really, really high. Okay, so that's a quick review about SVM and some of the questions we received in the last couple of weeks. Any questions? Okay, so let's move on to our new topic. Okay, now I want to talk about some practical concerns when using machine learning models. So let me tell you my plan in the next couple of weeks. So we finished discussing some of the most popular traditional machine learning models, including support vector machine, logistic regression, linear regression, Ridge and Lasso, KNN. And we haven't talked about decision tree algorithm, which I'm sorry, not decision tree, deep learning algorithm, which I will talk about maybe in the last month. But before I discuss the deep learning algorithms, I want to talk about some practical concerns when using the machine learning models. So the first one is one-hot encoding. When you have the categorical features, what should you do? So remember that in KNN, can you use categorical feature for KNN? The answer is it depends. It depends on whether you can define the distance between two categorical features or not. Right? For KNN, you need to find the k-nearest neighbors based on features and then make prediction based on the distance, based on the labels of the k-nearest neighbors. So if you can define the distance between two categorical features, perhaps you could use that feature for KNN. But if not, then perhaps you cannot use KNN. And can we use categorical feature for decision tree algorithm? The answer is you can, right? You basically group the features, group the instances into a couple of groups, and then trying to figure out which way to divide the instances will give you the purest result. Okay, so you could have categorical features. How about linear regression, logistic regression, and SVM? Can we use categorical feature or not? It's not clear how to use it, right? Because for this kind of models, we sort of need to compute. Let me open the. Okay. We need to compute like yi hat is some kind of like theta 0 plus theta 1 xi, for example. Right? For linear regression, logistic regression, SVM, you need some kind of computation like this. So if your feature is a categorical feature, it seems that it's not clear how to do this. Okay, so what can we do when we have categorical features? We will use something called one-hot encoding. Okay, so as an example, let's assume we have a feature called nationality, and we have 3 distinct values. Let's say we only have UK, Japan, and Mexico as this categorical feature. Sorry, I cannot find my code. Okay. So one way to do the one-hot encoding, we just basically assign, sort of converting this single feature into 3 features. Right? If we have UK, Japan, and Mexico, then we encode UK as 100, Japan as 010, and Mexico as 001. And that can be interpreted in this way. So for the first feature, that means UK or not. Okay, so if someone is from UK, of course UK is 1. Then second feature is Japan or not. The third feature is Mexico or not. Okay, so of course if someone is from UK, then UK is 1, the other 2 is 0. If someone is from Japan, of course this is 1 and the other 2s are 0, and so on. Okay, so it's sort of converting one single feature, one single categorical feature into 3 binary features. And someone might say that it seems that can I just use sort of like encode UK as 1, Japan as 2, and maybe Mexico as 3. I still keep using one single feature, but I encode UK, Japan, and Mexico as 1, 2, 3, for example. Can I do that or not? That's another way to encode the categorical features. You're sort of converting a categorical feature into a numerical feature. Can I do that or not? The answer is it depends. It depends on your learning model. If you use decision tree or random forest, then you can use this kind of encoding. Encode the feature into 1, 2, 3, for example. But if you're using KNN or linear regression, logistic regression, SVM, or even in the future we will teach the deep learning models, then usually we use one encoding. We don't use this kind of integer encoding. The reason is that I will give you some reasons here. Okay, let's think about KNN first. So for KNN, if we encode UK, Japan, Mexico as 1, 2, and 3, then essentially you are assuming that the distance between UK and Mexico is larger than the distance between UK and Japan, which may or may not be true. And if you change the order of the encoding, let's say you encode UK as 2, Japan as 1, and Mexico as 3, then the distance between these values become different. It seems that you should not let the way you encode the features to influence your result. Right. So that's one disadvantage of using if you just encode them as 1, 2, 3. Okay. How about for the let's say linear regression, logistic regression, or SVM? Okay. So again, if you encode UK, Japan, Mexico as one. Oh, here I use 0, 1, 2. That doesn't matter. Okay, if we encode UK, Japan, and Mexico as 0, 1, and 2, and let's assume we use logistic regression. Okay, so for logistic regression, let's say this is the feature of nationality. Okay, and if we use 0, 1, 2, then S can only be 0 or 1 or 2. Then in this case, the predicted Y can only be either one of these three cases, right? If someone is from UK, then you will end up having F of W0, this one. If someone is from Japan, you will have F of W0 plus W1. If someone is from Mexico, you will have this. Then again, if we assume that W1 is positive, then F of W0 is definitely smaller than F of W0 plus W1 and smaller than F of W0 plus 2W1. And again, this may or may not be correct. If we encode 0, 1, 2 into something like 2, 1, 0, then the order will be completely reversed. And again, we should not let the way we encode the data to influence the result. But if we use one-hot encoding, then the distance between, if we use one-hot encoding, then the distance between each pair of these two will be identical. And if we use the logistic regression, for example, then we will sort of, if we use one-hot encoding, then that will become your Y hat will become 1 divided by 1 plus e to the power of negative W0 plus W1 x1 plus W2 x2 plus W3 x3. And x1, x2, and x3 represents UK or not, Japan or not, and Mexico or not, respectively. So how important a certain nationality influence with your target will be characterized by this W1, W2, and W3. Okay, that's why we usually use one-hot encoding instead of using the integer to encode the categorical features. Okay, and if you if you go to the Kaggle competition, you will see a lot of different ways, interesting ways or creative ways to encode the features. Because one key recipe to win a Kaggle competition is feature engineering. So there are all sorts of creative ways to encode the features. And one way is called frequency encoding. So you just encode each category feature by its appearance frequency. Okay, let's say gender, you have male or female. If male appears, let's say, happen to be 2/3 of the time, female happen to be 1/3 of the time, they simply use this frequency as the feature value. Some people use this kind of encoding. So this is useful if the frequency is related to the target. And I'll give you an example. So if you want to predict the salary of an employee based on the rank, then usually a company has fewer high rank positions and they're usually well paid. And a company usually has many low ranked positions and usually their pay is not that well. So the salary might be inversely related to the number of such positions in a company. So in this case, perhaps using frequency could be a useful feature to predict the salary of an individual. Okay. So sometimes if we have two different categorical features, sometimes people would generate a new feature by combining these categorical features together. And then, in this case, you will end up having 4 distinct pairs. And then you just list all these pairs. Because sometimes, for example, let's say perhaps when feature 1 is B, feature 2 can only be N and cannot be something else. Sometimes that might be the case. Okay, so that's why sometimes people just combine the categorical features and compute the one-hot encoding after combining the categorical features. Transformation of the numerical features. So the first two are very popular way to sort of like scale the features. The first one is linearly scale the features into a fixed range. For example, -1 and +1, or 0 and 1. Okay, so if each feature is within a similar scale, then in KNN we have already seen that we need to sort of scale the features such that when we compute the distance is not dominated by a single feature. But even for linear regression, logistic regression, SVM, or even deep learning, we usually need to scale or standardize the features such that the scale in every feature is similar. The reason is that when we do the gradient descent, our next theta is our current theta, subject alpha multiplied by the gradient, right? And if every feature has a very different scale, then usually it's harder to find a single step size that works for every parameter. And that's why we usually need to scale the feature or standardize the feature first. So this is called scale the feature. And standardize essentially means you subtract the mean and divide by the standard deviation of that feature. Or if you believe that you have you have some outliers in your you have some outlier values for a certain feature, you could use this robust scaling. You subtract Q1 divided by Q3 subtract Q1. So if you have a couple of outlier features, that wouldn't influence the denominator. Or sometimes you need to compute the log or exponential to your feature, and that will make your features more or less like a Gaussian distribution. And here are the reasons why we need to scale or standardize the feature. I have already told you that for KNN, scaling the features will prevent the distance function being dominated by few features. And for linear regression, logistic regression, SVM, or even for deep learning, which will be discussed in the future, scaling the features will help numerical optimization. So let's think about it. If we have a certain y I hat, let's consider linear regression. Okay, let's assume that this is height, this is weight of an individual, which means that we want to use the height to predict weight. Okay. Then conceptually, if you use centimeter here and use the meter here, this shouldn't influence your result, right? Because if someone is 170 centimeters, that means he or she is 1.7 meters. If you change from 170 to 1.7, essentially you just need to, if for 170 centimeters, your theta 1 happen to be, let's say, 1, then when you change 170 to 1.7, you just need to change theta 1 from 1 to 100, then the result is equivalent. So it seems that we don't need to scale the features because the theta 1 is basically just, you scale the theta 1 to the inverse direction, you will get the same result. So it seems that for linear regression or logistic regression, it seems that we don't really need to scale the features. But the reason that we still need to scale the features is because when each feature is in a similar scale, then numerically, it's easier for us to find the good thetas. That's for numerical computational reasons. So if someday we can have a new way to find a theta, which doesn't depend on gradient descent, we just happen to have some way to find the thetas directly, perhaps we don't need to scale the features. But now, because we still heavily depend on gradient descent to get the thetas, which is a numerical way to get the thetas, then we need to scale the features first. Okay, so it's 2:51. Let's have a 10 minutes break. I'll come back at 3:01. Okay, let's continue. So we said that for linear regression, logistic regression, SVM, or even for deep learning, we need to scale the features for numerical reasons. And then if you are dealing with decision tree or random forest, then scaling or not is not important. That doesn't influence your result. Okay, next, we also, in the last couple of slides, we said that sometimes we need to compute the log or exponential to the features. And so if your feature is positively skewed, positive skewed means that you have a lot of features with low, for a certain feature, you have a lot of smaller values, but you also have a couple of very large value. And so if that is positively skewed, then when you compute a log to every of these, to all the feature values, then the distribution will become more or less Gaussian-like. If your feature is negative skewed, then by computing the exponential, again, it will more or less Gaussian-like. And here is just a sort of like a small trick. If your feature is between 0 and 1, then you should use 1 plus x and then computing the log. The reason is that the log function is something like this, right? Okay, so if you just compute the log, then for example, log 0.1 will be smaller than 0. And if you want to keep your feature to be positive, then perhaps you should add 1 in the front. Okay, another trick is thresholding and ranking. Okay. Thresholding is essentially means that when the feature is larger than a certain threshold, then output is 1, otherwise it's 0. Sometimes you just care about whether something is large enough or not. Perhaps that's what really matters. Then you could use this thresholding. Or you could rank the features. Ranking means that perhaps you don't care about like the absolute value. You just care about which one is larger, which one is smaller. Okay, so if you have 10,000, 0, and negative 1,000, they become 2, 1, and 0. If you have 0.1, negative 0, 0, negative 0.005, and pi, then they become 1, 0, 2. That's another way to do it. And of course, you can further scale it such that the value is between 0 and 1. Okay, there's yet another interesting technique. Okay. When I first saw this technique in a Kaggle competition, I cannot realize why they want to do this very strange encoding. But I found some people give this explanation. So I'll tell you what that means. So it said if you have a certain feature whose value is 3.99, you should separate, you should sort of keep only the integer part or keep only the fractional part. Okay, so if you have 3.99, it becomes two features. One is 3, one is 0.99. Okay, and this sounds very strange. Why dividing a feature into the integer part and the fractional part? And here's an explanation. They said that you might be able to capture humans' subconsciousness of the numbers. So people say that when you see the price, 3.99 and 4 are very different. 4 means it's more expensive. 3.99 perhaps means it's not that expensive. Right? So some people just separate this into the integer part and the fractional part. And you can put this into like even more extreme. If you have, let's say, 771.585, for example, I just randomly write a number. You could sort of say, convert this into 1 and 0 and 0 and 0 and 1 and 85 as 1, 2, 3, 4, 5, 6 different features. Right, so again, this might be able to capture some kind of subconsciousness of human. Okay, this is yet another very interesting way to convert numerical features. It's called Gauss rank. And this feature is, this technique is proposed by this person who won a big competition a couple of years ago. And in this competition, he won the competition, and he doesn't really use any fancy models at all. He used some of the popular models, but nothing fancy. But he proposed one way to encode the numerical features, which turned out to be very useful for this competition. Okay, so I'll tell you what it is. And I only saw this technique in the Kaggle competition forum. I have never seen anyone discuss this technique in, let's say, papers. So using this technique, you can convert any numerical feature into Gaussian shape. No matter what the original distribution is, you can always convert it into Gaussian. But whether this is good or bad, that depends. Okay, that could be an issue. But if you really want to convert a numerical feature into Gaussian shape, this will guarantee you to do that. So I'll tell you the procedure, but I don't plan to tell you why it works like this. If you really want to know why it works like this, we could discuss offline, or you could take another course. I will discuss this method in more detail in another course, but I don't plan to tell you the math details in this course, because that would take another, I guess, perhaps 30 minutes or 1 hour to explain why it will work like this. So I'll just tell you the procedure. So first, you need to sort the original features using the order to replace the original feature value. So that means if you have something, so that's sort of like this ranking here. You convert this into 2, 1, and 0. Okay, you just use the ranking to replace the original feature values. That's step number 1. And step number 2 is you scale the order values to be within -1 and +1. Okay, so for example, if you have, let's say, for a certain feature, let's say height of an individual, and let's say we have 5 people, their heights are 140, 180, 170, 160, and 150. Okay, we have 5 people. Then in the first step, we just rank them. So who is the shortest? Oh, this one is the shortest. This one is the second shortest, third shortest. This is the second highest, this is the highest. Okay, so we use the order to replace the original feature value. Then we convert this to be between -1 and +1. So that means this one will become -1. This one will become +1, and the others are just within this range. Okay, so they will become, this is -1, this is +1, and this is 0, this is 0.5, this is, I'm sorry, this, let's see, this is -0.5, this is +0.5. Okay? And, oh, by the way, I made a mistake here. So it cannot be exactly +1 or -1. Then otherwise, later on, there will be a problem. So it has to be very close to -1, but it cannot be -1. Okay, so this could be, for example, like -0.999. And this can be for 0.999, something like this. And they cannot be exactly -1 or +1. Otherwise, there will be a problem later. Okay? And then, once you have these features, you just apply a special function called Earth inverse. That's a special function. But anyway, it's just a function. You plug in these numbers to this function, it will give you an output. Okay? It's just a function. And after you apply this Earth inverse function, the feature distribution will become Gaussian, magically. And I don't plan to tell you why. I just tell you the procedure. And but I will give you an example. I did this example just during the just this morning. So here I generate a feature, and the distribution is, it has double peak. So apparently it's not a Gaussian distribution. Okay, it has double peaks. I essentially combine two Gaussian distributions. The first one is has mu1 and variance 1. The second one has mu5 and variance 1. And for each Gaussian distribution, I generate 1,000 samples. Okay, so this one, the first Gaussian here, the mean should be roughly 1. For the second Gaussian here, the mean should be roughly 5. Okay, so the feature is indeed not Gaussian. And then I just compute the rank. Okay, so if your feature is like this, then you plug in this x to this function, the output will be 5, 3, 1, 2, 4. Okay, so I essentially just obtain the order of these numbers. And then next, okay, so I just finished the above two steps. And the next, I just scale the features such that it's between -0.999 and +0.9999. Okay? And then I plug this into the Earth inverse function. And I plug the distribution, and it's Gaussian-like. Okay, so I just tell you the procedure to do it, but I don't plan to tell you why it works like this. If you want to know if you are really interested, I could tell you some keywords, and you can study this by yourself. It's called, what's the name of it? I suddenly forgot about the name. What's the tech? It's inverse sampling. It's called inverse sampling. It's sort of a technique to generate Gaussian distribution, but I don't plan to tell you the details. If you are interested, you could use this as a keyword to and search on Google or something. Okay, how to deal with missing values? what's going on. If the type of feature is a categorical feature, so how to deal with until now we always assume that you observe all the features. If you're given an instance, you can observe all the features, but very often you probably miss something. And one way to deal with missing value is you just ignore that sample. Okay? If you want to use height and weight to predict something, and you happen to misrecord people's height, then you just ignore that sample. That's one way to do it. Or you could use, if your feature is a categorical feature, then perhaps you could replace the missing value with the most frequent value. And that's one simple way to do it. Or your feature is a numerical feature, then perhaps you could replace the missing value with the mean or median of that feature. And of course, there are some more advanced techniques which try to sort of predict the missing values. And of course, you can use those kind of techniques. But if you predict the missing values and you use the predicted missing values to predict your target, and if your result turns out to be not that good, it's really hard to tell which part goes wrong. It could be your model is okay, but you incorrectly predict the missing values. But anyhow, so it's really hard to tell which part goes wrong. So sometimes people just use the first two techniques. Okay. Next, imbalanced classification. Okay. So if you're dealing with the classification problem and you found that let's say, for example, binary classification, and you happen to find that the positive class contribute to 99% of your training data, and your negative instance only contribute to 1% of your training data. Some algorithms, in this case, might tend to predict most of your future predictions as positive, because it found that whenever I predict something as positive, I seem to always right. Alright, so in this case, some people might use undersampling or oversampling on the training data. So undersampling means that you sort of undersample the majority class such that the size of the positive instance is approximately equal to the size of the negative instance. Or you can oversample the minority class, which means that you just repeatedly sample the minority class. And then such that the size of the positive instance and the negative instance are roughly the same. And do the training after that. Oh, and by the way, you can only do the undersampling or oversampling on the training data. You cannot touch the test data. You cannot oversampling or undersampling the test data. Otherwise, you sort of use a distorted samples to measure your algorithm. So you can do any tricks you want on the training data, but you cannot change the proportion of the test data. Okay. Next issue, selecting the hyperparameters. Okay, so we talked that for the different algorithms, there are some hyperparameters like the K in KNN, the C, or sometimes we use lambda for the regularized linear regression, or sometimes, or like the step size for gradient descent, that could also be a hyperparameter. So how to decide these hyperparameters? So first, I think in KNN we discussed that if you really know these algorithms, then you should know the role of these hyperparameters in that algorithm. So for example, in KNN, when K is small, you tend to overfit the training data. When K is large, you tend to underfit the training data. So how to select these parameters? If you want to systematically investigate or system, if you want to have a systematic way to decide the hyperparameters, then essentially you should, based on the experimental result, you should determine whether you are overfitting or underfitting currently. And then based on this information, you decide whether you should increase or decrease the value of these hyperparameters. Ideally, you should do that. But in certain cases, sometimes you really don't know that algorithm. And you just know that there are certain hyperparameters you can fine-tune, but you don't really know the relationship between these hyperparameters and the models. In that case, what can you do? So then there are some strategies, grid search, random search, or Bayesian optimization. And I don't plan to talk about this in detail because I will talk about this again in my another course. If you are interested in this kind of topics, you can take my another course in the future. But anyhow, I will tell you grid search and random search. So grid search is essentially just a fancy name for exhaustive search. Basically, you just try different values for a certain hyperparameter and see which one gives you a good result. And random search is just randomly pick some values for that hyperparameter and see which one gives you a good result. So let me give you a visual example. Suppose for a certain algorithm, you have two different hyperparameters you can use. Okay, here represent hyperparameter number one. For example, you set a certain hyperparameter to 0.1, 0.5, 0.9, for example. You try three different values for a certain hyperparameter. And this is for the second hyperparameter. Again, you try some different value. Let's say 1, 10, 100, for example. You just try some values for different hyperparameters. So if you have two different hyperparameters and for each one of them you pick three values, then you will end up having 9 pairs. You will try 9 pairs. You will build nine models based on 9 different pairs of hyperparameters. You will see which one gives you a good result, and you will just pick that hyperparameter set. That's that's grid search. For random search, you just randomly pick 9 different pairs and then see which one gives you a good result. And if you compare these two, which one is better? Several years ago, when I first saw these two methods, my intuition told me that grid search is probably a better idea. That's my intuition. I don't know about you, but that's my intuition. But it turns out that random search is better. And I'll tell you one intuition about why random search might be better. So for all the different hyperparameters, usually only few of them really matters. Only few of them really influence your result. Most of them doesn't really influence your result that much. Okay? So let's assume that for these two different hyperparameters, this one is an important hyperparameter. Whether it's 0.1 or 0.5 or 0.9, that really matters. And the other one doesn't change that much. Okay? So for the first hyperparameter, when you set a different value, when you give it different values, they will give you different, let's say, accuracy. Right? So that varies a lot. For the second hyperparameter, no matter which one you give, no matter which value you pick, they give you roughly the same result. So if we use grid search for this important hyperparameter, you only try 3 different values. But if we use random search, then for this important hyperparameter, very likely you will try 9 different values. So that's why random search usually gives you a better result. And this is reported in this paper, which is written by Yosha Bengio. Yosha Bengio is one of the most prestigious researcher in deep learning. In fact, Yosha Bengio and Yang LeCun and Yosha Bengio, Yang LeCun, who's the third guy? Geoffrey Hinton. These three researchers, they won the Nobel Prize. I'm sorry, not Nobel Prize. They won the Turing Award a couple of years ago for their fundamental contribution on deep learning. So they are sort of like the Nobel Prize class researchers. Anyhow, in this paper, they said that a random search is better. Okay, and okay, and so if you want to decide which hyperparameter is good, then you need to do the validation based on not the test data. If you report the, for example, accuracy based on test data, that's a over-optimistic estimation. So that if you really need to fine-tune your hyperparameter, you need to fine-tune your hyperparameter based on validation data, which we haven't talked about yet. So previously, we always say that you divide your label instance into training and testing. You build a model on the training data, and you report your performance on the test data. But this is not the case when you have hyperparameter to fine-tune. If you have hyperparameter, you want to fine-tune your hyperparameter, you cannot fine-tune your hyperparameter based on test data. Otherwise, you are sort of overfitting your test data. So if you have hyperparameters, you need to fine-tune. You need to divide your label data into three parts: training, validation, and test. And you use the training data to build different models based on different hyperparameters. You validate which hyperparameter is better based on the validation data. And once you decide the best hyperparameters based on the validation data, you need to fix it. And then you merge training and validation data together as the training data. And train a model based on the new training data using the hyperparameters you just selected. And then finally, you evaluate the performance based on test data. Then that would be a reasonable estimation. Otherwise, there would, if you don't use this, if you just divide your data into training and testing, and you decide the hyperparameter based on test data and report the result directly, that would be an over-optimistic estimation. Okay, so this is just write down what I told you. Okay, so perhaps let's use this figure to explain it. To explain again, let's say you have, for example, 10,000 labeled instances, and let's say you put 3,000 of them as test data, 7,000 of them as training data. And if you really need to fine-tune your hyperparameters, then perhaps you could use 5,000 of the training data as the training data, and the other 2,000 of them as the validation data. And still you have 3,000 of them as the test data. And let's assume that you want to use, for example, KNN model. And you just don't know how to pick this K, because you don't know, assume you don't know KNN model, and you don't know what's the relationship between K and the model. And so in this case, you want to find a good K. Then what could you do? You use these 5,000 training instances to build several different models using different Ks. So for example, K is 1, K is 2, up to, for example, K is 10. You use the 5,000 training data to build 10 different KNNs, where K is 1, 2, 3, up to 10. Then you will end up having 10 models, model 1, model 2, up to model 10. Then you feed this 2,000 validation data into these 10 models and see which one give you the best result. Let's say K equals 2 give you the best result on the validation set, for example. And let's say in this case your accuracy is 97%, for example. If you directly report that KNN K equals to 2 will give you accuracy 97%, this is an over-optimistic estimation. A more reasonable estimation is that if you found that K equals to 2 is the best hyperparameter based on validation set, then you should combine the training data and the validation data together and build a KNN model where K equals to 2. And then after you build this model, you can finally, for the very first time, you can finally use the test data. You just feed the 3,000 test data into this model and see what the accuracy is. And that's a reasonable estimation. Why cannot, if you just report, let's think about another case where you don't have the validation data. Let me remove everything. If you don't have the validation data, you just have, let's say, 7,000 training data and 3,000 test data. And you just use these 7,000 instances to build K equals 1, K equals 2, up to K equals 1,000. And then if K equals 2 give you the best result, this is sort of like you happen to find a hyperparameter that's particularly good for these 3,000 test instances. So that's an over-optimistic estimation. So in other words, you should leave your test data alone. You cannot touch it until everything is decided. Then for the very first time, you can touch the test data. During the entire training process, the entire hyperparameter fine-tuning process, all these processes, you cannot touch the test data. If you fine-tune your hyperparameter based on your test data, then you are sort of trying to overfit the test data. You try to find a good hyperparameter that's particularly good for your test data. So that's overfitting. You cannot touch your test data at all until everything is decided. Okay, so okay. So I think I have some. I will skip this couple of slides, but let me tell you cross-validation, and I'll skip the last couple of slides. So cross-validation, this is relevant, but not the same as the training, validation, and testing split. But many people confuse them, probably because cross-validation has the word validation, and training validation testing also has the term validation. So cross-validation, this is a technique to evaluate the model when you have limited training instances, or when you have limited labeled instances. If you have a large number of labeled instances, then this technique is you can ignore this technique. But if you have very limited number of labeled instances, cross-validation will become very important way to evaluate your model. So let's assume you have 100 label instances. Then we assume that you don't have hyperparameters, so we just need to divide the 100 label instances into training and testing. Okay. So assume that you have 90 of them as training and 10 of them as testing. Okay. And because you only have 10 test cases, if you are lucky, you happen to correctly predicting one more case, then you have 10% boost, right? Because if you have 3 of them are correct and 4 of them are correct, that's very different. 30%, 40%, that's very different, because you have limited testing instances. So some people might say that, then can we, instead of having only 10 instances, can we have, for example, like 50 test instances and 50 training data? But in this case, you have limited training data, right? We always want to have more training data to prevent overfitting. So this is sort of like a trade-off between the number of training instances and number of test instances, because we have only 100 very limited label data. So we have this dilemma. So k-fold cross-validation is trying to fix this issue. So we divide these 100 instances into 10 different folds. Each fold has 10 instances. Okay, so let's say we divided 100 samples into 10 folds. Okay, 1, 2, 3, up to 10. And each fold, the first fold has instance number 1, to instance number 10. The second instance has instance number 11 to number 20, and so on. So the last one has number 91 to number 100. And k-fold cross-validation is, in the first round, I use the first fold. This is the first fold as the test data, and the other folds as the training data. Okay, so in the first round, I use the top 10 the first 10 instances as the test data. That's the first round. And in the second round, I use the second fold, which means number 11 to number 20 as the test data, and the others as the training data. In the third round, I use the third fold as the test data, the others as the training data. Okay. So I would do this for 10 rounds. And for each round, I use one fold as the test data, the other 9 folds as the training data. So eventually, I would have 10 results, and I just compute the average of these 10 results as my final estimation of the accuracy. So you can see that whenever, if the result is, let's say, 90% accuracy, this 90% is the average of 100 test instances. So if you happen to have, if you get lucky, you have one extra correct guess, they only influence 1% of the accuracy. Okay? So, and every time when a certain instance is in the training data, it will not be in the test data. So we don't have the issue of sort of like picking the answer. We don't have that issue. So that's cross-validation. And there are a couple of types of cross-validation. What I just told you is called the k-fold cross-validation. You divide the data set into k different folds to do the validation. And there are some other variations. One is called leave one out, which k equals to, So leave one out is essentially if you have 100 instances, then you just set the number of folds to 100. Okay, so every time you just leave one as the test instance, the others are training instances. Okay, that's just one variation. Or leave p out. which means that P out of N are regarded as the validation data for each round. Okay. Certification. This means that for each split, you need to assure that for each fold, the number of positive and the number of negative instances are roughly, their ratio are roughly the same as the ratio of the entire training population. And for time series data set, you need to be, let me check if I have a figure to explain that. Yes, I do. Okay, so let me tell you what that means first. So for time series data, like for example, predict the stock price, for example, you need to divide your data set sort of like in the sequential order. What I mean is that let's say X1, Y1 is, let's say, based on the first day's feature, you want to predict the stock price at day 1. And X2 and Y2 are the feature and target of a stock at day 2 and so on. And if you want to split the data set into training and testing, you need to divide. You cannot just randomly pick some of them as the training, the others as testing. What you should do is keep the older data as the training data and the later data as the test data. You cannot use something like you use X1, Y1, and X3, Y3 as the training data and X2, Y2 as the test data. Otherwise, because this happens in the future of this. If you put this in the training data, it is possible that this includes some information that may help you to decide the values here. So, if your data is some kind of time series data set, you should put the old information in the training data and the new information in the test data. Let me skip this slide. Let me skip the last couple of slides. Okay, and for multi-class classification, we talked about this already, right? For multi-class, how to apply binary classifier on multi-class classification. So we have the one versus stress and the one versus one method. So we talked about this already. So I'll skip these slides. Okay, finally, bias versus variance. So very often when you apply a certain machine learning algorithm, a certain supervised learning algorithm on your problem, very often in your first version, usually you will see that the result is not that satisfactory. You probably need to do some modification. So what's a reasonable next step? Then you should consider the bias versus variance. So the test error is in fact comes from 3 parts: bias or variance or noise. And unfortunately, we cannot control the noise because noise is sort of embedded in the data already. So what we can control is this bias versus variance. So what is bias? So let's assume that F is the true relationship between X and Y. X is the feature, Y is the target. Okay. And F is the true relationship between X and Y. And this H is your hypothesis space. A hypothesis space is like based on your model, what are all the possible relationship between X and Y based on your model. So for example, if you assume that Y is theta 0 plus theta 1x. If this is your model, then of course, if the true relationship between x and y is, let's say y I hat is in fact log xi, then of course, no matter how you fit the data, you cannot get this true relationship between x and y. So the distance between the true relationship between x and y and your hypothesis space, that's called the bias. And what is variance? Variance is because you have only limited data set. You don't have like all the data set. So based on the limited data set, what's the best model you could get based on the limited data set? And if you have infinite data set, you might get a better theta 0 and theta 1. But because you have only limited data set, you cannot get the best theta 0 and theta 1. So distance between, you have perfect data and you have only available data, the distance between these two is the variance. Alright, so let me give you a more formal definition. So D is the training data set. And let's say GD is the predicting function after training on the training data. And G bar is assuming you have infinite training instances. Then what's the final model you could get? Okay. So the distance between this GD and G bar here, the distance between these two is the variance. Okay. So let's say again, if you assume that if you assume the relationship between y hat and y is theta 0 plus theta 1 xi. If you have only s1, y1 up to sn, yn as the training data, versus if you have x1, y1 up to x, let's say 1000 n and y 1000 n as your training data, then usually this one will give you a better result because you have more training data. And if this n keep increasing to like infinity, okay, then of course this one will tend to give you a better result. Okay, so the distance between these two is called the variance. Okay, and it's measured here. Okay, this is assuming you have infinite data. What's the model you will get? This is because I only have this much data. This is the model I could get. The difference between these two is called variance. And it's 3:51. Okay, so let's have a 10 minutes break. We'll come back at 4:01. Or may not contain the true relationship between x and y. So this f of x is the true relationship between x and y. So the distance between these two is called the bias. So for example, we just said that if the true relationship between, if this f of x is in fact simply log x, the true relationship between x and y is this. And if you somehow assume yi is theta 0 plus theta 1x, well, then of course you cannot get, no matter how many training instances you have, you still cannot get this true relationship. So this distance is called the bias. And if you have a very large hypothesis space, then usually your bias becomes smaller because you are more likely to include the true relationship between x and y. But in this case, usually your variance becomes larger. On the other hand, if you have a very small hypothesis space, then you usually have a larger bias but smaller variance. So, how to decide whether you should have a model with larger hypothesis space or not? Or should you label more, should you have more label data as the training instance? So let's look at the relationship between first, model complexity and the prediction error. Okay. When you have more and more complex model, and so now we assume that your training instance is fixed. Your training instance is fixed. When you have more and more complex model, your training error becomes smaller and smaller. But your test error will become smaller first and then become larger. Okay, so here, when you have a small training instance but large testing instance, you are likely to overfit the training data. On the other hand, if both the training and testing instances are, if both the training error and test error are large, then you are likely still underfitting. Okay, so this is the first relationship. Given fixed training instance, what's the relationship between error and model complexity? Let's look at the second figure. When your model is fixed, as you have more and more training data, what's the relationship between training error and test error? So if your model is fixed, and if your training data is, the size of training data is small, then your training error is usually smaller. This is obvious because, well, if you have only one training instance, for example, you want to fit that single training instance, that should be very easy. But in this case, because you only fit the thetas, for example, based on single instance, then it is very likely that this theta is not a good theta for the other unknown, unseen data sets. And so in this case, usually your test error is high. As you have more and more training instances, your training error will gradually become larger and larger, and eventually it reaches a certain value. And your test error will become smaller and smaller. Okay, so that's a trend. So if we consider these two figures together, one is the relationship between model complexity and error. The other is training size and the error. Then we will come up with a sort of like an SOP to decide what's a proper next step if your model is not performing that well on the test data. Okay, so this SOP, sort of like SOP, it's from Andrew Ng's talk in 2015. Andrew Ng is he is a professor at the CS department in Stanford, and he is also a co-founder of what's that platform? He's a co-founder of Coursera, and he was also a research head of Google's Google Brain, which is a research institute in Google. He was a director in Google Brain, and he was also a director of Baidu a couple of years ago. So anyhow, he has a lot of experience in both research and engineering, and he said that. So he probably supervised maybe dozens of projects simultaneously when he was a director of Google Brain or when he was at Baidu. And he said that for most of the time, when he reviewed those projects, he was thinking about this diagram we are going to introduce. Oh, by the way, so I put a rocket here because he said that for a supervised learning project to be successful, it's sort of like to successfully launch a rocket. To launch a rocket, you need two components. One is your engine has to be powerful enough. The other is you need to have enough fuel so that it can launch. And so he said that to have a powerful engine, that's sort of like to have a powerful model. To have enough fuel, that's sort of like to have enough data. So this is the SOP we are going to introduce. So the first step is you need to check whether your model is performing well on the training data. if your model is not performing well on the training data, that means even for your model have already seen this training data but still make incorrect prediction, which means your model cannot find the right relationship between X and Y, even it sees those training data. So you need a more complex model in this case. Okay, so first you need to repeat this loop until you believe that your model is performing good enough on the training data. So for example, if you believe that 90% should be good enough, then at least on the training data you have to be 90% correct. Then you can move on to the next step, which is your model performing well on the test data or not? If your model is performing well on the test data, then of course you can probably launch your product. But usually, it's very likely that your model is performing well on the training data, but probably not that well on the test data. In this case, you have two possible ways. One is make your model a little bit simpler, because your model is currently performing well on the training data, but not that well on the test data, which means you are overfitting. So solution number one is you make your model a little bit simpler to prevent overfitting. But if you're in your scenario, you can collect more label data as your training data. Then Andrew Ng suggested that you should collect more label data as your training data, because more training data would also help prevent overfitting. Okay, so he suggested that if you can collect more data as the training data, you should collect more data and go back to the first loop here. And let's compare this SOP with the previous two slides we just shown you. So in the beginning, when your model is performing poorly on the training data, you are probably still in this stage. So you should make your model more and more complex such that your training error will become smaller and smaller. But it is possible that like if you believe that your model should be 90% correct, or your error rate should be 10%, then perhaps 10% is here. All right? So in this case, you started to overfit your test data. So your training data is performing very well, but your test data is not that well. And then in the next step, you should collect more data, because now you have a good training error, but not that good test error. By increasing the size of the training data, you would decrease the test error. Okay, so that's why he said that you should repeat these two steps until you have good performance on the training data and good performance on the test data. But this scenario is sort of like in the industry. Perhaps you could collect more data as the training data. But if you are, for example, participating in the Kaggle competition, then in those competitions, you usually cannot obtain more label data as your training data. You usually have a fixed training data set. Then in that case, you probably cannot collect more data as your training data. So in that case, to prevent overfitting, you probably need a lot of different models and sort of combine them together to prevent overfitting. Or perhaps you should use a simpler model to prevent overfitting. But in industry, if you can collect more data as your training data, perhaps you should follow this SOP. Okay, so for model selection, of course, your domain knowledge is important. If you know that the relationship between X and Y is linear, then you should use linear relationship. Data size is important in certain cases. If you apply complex model on small data, then you would overfit the training data. Then in this case, collecting more data will be helpful. On the other hand, if you apply simple model on massive data set, you will still underfit the training data. In this case, even if you collect more label data as training data, it won't help. it won't help. Okay, so when will data size important? If you are overfitting, then collecting more data will be very helpful. If you are still underfitting, then collecting more data will not help your testing accuracy at all. So for algorithm, you should select algorithm that is complex enough to find the relationship between x and y. But meanwhile, if you have only limited data set, then an over-complex model might overfit the training data. Okay, so I guess that's all I want to talk in terms of the practical concerns. So let me ask you a couple of questions before before we close this topic. First question. If you find that your model performs well on the training data but poorly on the test data, and if you can only choose between increasing the model complexity or decreasing the model complexity, then should you increase or decrease the model complexity? So performing well on the training data but poorly on the test data, that means you overfit the training data. So that means your model is too complex. So if you can only choose between increasing or decreasing the model complexity, in this case, you should decrease the model complexity. Okay, next question. Is collecting more data helpful or not in this case? The answer is it will be helpful in this case. When you overfit the training data, collecting more label data as the training data will always be helpful. Next question. If you find that your model performs roughly the same on training and testing data, and you believe that the current accuracy is still not good enough, then in this case, collecting more data will be helpful or not? The answer is it won't be helpful. Let's go a couple of slides back to look at the trend. It's sort of like in this case, your training error and test error performs roughly the same, but you believe that this is not good enough. In this case, even if you collect more training data, the test error would roughly still the same. So that won't be helpful. If we increase the model complexity and collecting more training data, then this will probably be helpful. Okay? Because now you believe that your model performs roughly the same in training and testing data, and you believe that's not good enough. Then by increasing the model complexity, you will make your training error become smaller, but your test error becomes larger, which means you will overfit the training data. You are likely to overfit the training data. And in that case, you collect more data as the training data, which will help you to prevent overfitting. Okay, so if you do these two steps simultaneously, it is possible to make your test error smaller. Okay, next, let me ask you one scenario, which is a typical scenario if you are writing a research paper. Okay, so you find a problem, and you collect the experimental data for that problem. And you propose a method for that problem. And you compare your proposed method with the previous method based on the collected data set, which is very typical workflow for many students to write a research paper. And if you're step number 4, you found that your method is worse than the previous method, then you go to step 4 and try different hyperparameter for your method. And you just repeat this process until you find a good hyperparameter. Is this a fair process or not? Of course it's not, okay? Because you are sort of trying to find a hyperparameter that overfits the test data. Okay, so this is not a proper way to do a research. Unfortunately, I believe many of you using this workflow to write a research paper. This is not a proper way to do a research. If you really want to go to step 4, but I can understand that if you only have limited label data, of course sometimes you cannot avoid this if you only have limited label data. But you need to know that if you observe something based on the test data, and you include that idea back to your model, of course your model will become better on the test data. Okay, so you need to aware that if you really do this, you are short of overfitting test data, unless that idea has some valid, that idea has some reasoning. Okay. Okay, so that's all I want to talk about practical concerns on supervised learning. Let me check if there's any questions on the YouTube. Yang LaCun also win 2019. Oh, really? Yang LaCun also win two. Is that the year? One student in the chat room said that Yang LaCun won 2019, I believe, Turing Award. Is that the year Yang LaCun, Yoshua Bengio, and Geoffrey Hinton won the Turing Award? I'm not sure. You could Google it. Okay, or is it that Yang LaCun win some other prizes? If you know that, you could leave in the chat room. Okay, so let me move on to the next topic. Okay, next I want to talk about recommender systems. And I want to talk about this topic for a couple of reasons. The first is that you will see very soon that the setting of this problem may look different from what we have learned so far. So for most of the time this semester we talk about supervised learning. And you will see very soon that the setting of this problem doesn't really look like the supervised learning problem. But it turns out that after some sort of modeling, we could leverage the techniques we learned so far to solve this problem. Okay, so that's the first reason I want to introduce this. And the second reason is that a couple of years ago, I think perhaps 2017 or 2018, one of my graduate students who studied recommender system, and he proposed an interesting idea that could solve a so-called CoStar issue in recommender systems. And I will tell you what that issue is after we discuss CoStar. And also, the idea is simple, but I believe if you follow most of the content so far, you can understand that idea. And it turns out to be a simple technique, but turned out to be useful, and I want to show you that. So that's two reasons why I want to talk about recommender systems. And okay, so for recommender system, there were two important historical events that makes this topic popular in both industry and academia. One is Amazon. Back in 2000, Amazon was originally only sell books. If you know this, I don't know if you know that story. They originally only sell books. and they hire a lot of editors, human editors, to sort of write the comments for the books and try to recommend books to different people based on the editor's knowledge. That's back in 1990 something. And in year 2000, Amazon tell people that they use machine learning algorithms to build recommender systems, and those recommendations are better than human. So people start to realize that recommender system based recommendation based on machine learning could be very powerful. And the second very important event is Netflix. In 2006, they announced a competition called Netflix competition. And the first winner of that competition can won $1 million US. That's a lot, and that's in 2006. So a lot of people go to that competition trying to win that $1 million. So anyhow, let's look at why Netflix might be very interested in recommendation, especially in early days like 2006. So I don't know if you know that Netflix was originally not a video streaming company. They originally sent DVDs, the real DVDs, to your home. Not like the now they do the video streaming. So they need to have a very huge warehouse for the DVDs. Right? They need to have a real warehouse. And it's very difficult to manage the warehouse. So on the one hand, you know that the popular DVDs, the hot DVDs, people might like those DVDs. Most people might like those DVDs, but the very popular DVDs, Netflix may need to pay more money to the companies to get the very popular DVDs, and if they sort of rent those popular DVDs to everybody, then they need to have a huge number of those popular DVDs. On the other hand, they might have a lot of less popular DVDs in their warehouse. Okay, so if they could somehow identify who might like which unpopular DVD, there might be a huge help for their business, because they probably don't need to store that much DVD on their warehouse. They could send all the DVDs to the right people. And meanwhile, they probably don't need to pay a lot of money to the DVD producers, to the movie producers, because they are less popular after all. Okay, so if they could buy a lot of less popular DVDs, but meanwhile they know who will like which DVD in particular, then that might be a huge business for them. So in the very early days, they really need to know who like what. Now this is probably less important, because if you see something you don't like, you just skip it. You can get the next movie right away nowadays. So this is probably less important. I guess that this is less important for now. But back in 2005, 2006, this is huge for them. They need to send the right DVD to you. Otherwise, if you receive a DVD you don't like, you probably think Netflix doesn't help you. You will stop the subscription. They will lose a customer. Okay, so anyhow, they want to recommend the less popular DVDs to the right people. And because of that, they have a algorithm in-house. They call it Cinematch. And Cinematch is they try to guide the customer to avoid the hot movies. They want to they want to select the less popular movies, but you may like it. And so the core technology of Cinematch is that it's a 5-star rating system. And they group users with similar tastes together. So they check their warehouse every hour and pick the available movies or the available DVDs to the right customer. Well, that's essentially what Cinematch does. Okay, so this is a little bit about the history. And now let's talk about the Netflix prize. So in 2006, they launched this competition. And because they already have a Cinematch, which is their in-house recommendation algorithm, it predicts who will like what movie. So they said that if you can drop the room mean square error by 10% compared to their Cinematch algorithm, you will win the prize. So it's not that like, so if you take the Kaggle competition, it's usually like, let's start today, and after 3 months, let's see who get the lowest room mean square error. That's a winner, but that's not in this competition. That's to win this competition, you have to lower the room mean square error by 10%. So it's not like in 3 months who get the lowest RMSE, who will be the winner. So it is possible that if there's a team who can reach this criteria in 1 day, you will get $1 million like in 1 day. But it is also possible that after 1 year, no team reach this criteria. It is also possible like that. So they have a sort of like the best result of the year prize. If after 1 year, nobody reached this criteria, the first team of that year can still get 0.5 million. So it turns out that it took 3 years for the first team to reach this criteria. So this competition lasts for 3 years. This is a summary of this data set. They have 1 million ratings from nearly 500,000 users. They have nearly 20,000 ratings. Nearly 20,000 items. And they give you this training data, and the goal is to predict the last few ratings of each user. So you have the predicted ratings, and they know the ground truth, so they can compute a room mean square error for you and compare the room mean square error you predicted with their Cinematch. And here are some of the statistics in this data set. They found that, so based on the probing data is the last few ratings in the training data. They call it prob data. It turns out that the statistics of the prob data is a little bit different from the training data. And they also found that based on the data set, on a certain date in 2004, people's ratings start to increase. Certain event happens around this time, but we don't know what that is. But anyhow, based on the data set, people after that date, people are more satisfied with their recommended movies. Perhaps, I don't know, perhaps they changed their Cinematch algorithm or what. So perhaps Cinematch algorithm becomes more accurate at that date. So people started to be more satisfied with their received DVDs. Oops, okay. And here are some of the statistics on the movies. These are the movies that received the highest average ratings. So this one is in Chinese, 刺激1995. This one is in Chinese, 魔戒. This one is 绿色奇迹. This one is another 魔戒. This one is a Disney movie. What's the name of it? 海底总动员. Thank you. And this is a very old movie. I guess most of you probably didn't watch this movie because you are too young. This is called 法柜骑兵. This is a movie in the 1980s. When I was a kid, this is a very huge movie. Anyhow, so these are some of the movies that received the highest ratings, and these are the most rated movies, which means a lot of people rated this movie. But most rated movie is not necessarily the highest rated movies. These are the movies with the highest variance, which means a lot of people like these movies and a lot of people don't like these movies. Oh, by the way, if you believe that there should be certain movies on the top list but not on the list, it's probably because this competition was launched in 2006, which means that all these movies here are released before 2006. Okay, so there are certain quite nice movies in the last decade that they were definitely not on the list. These are some statistics on the users. So, by the way, there might be some error on the data set because for this user, if he or she wants to rate this many movies, on average, he or she needs to rate more than 5,000 movies a day. So apparently, there might be some problems in the data, but this is what they released. And so, as I said, this competition lasts for 3 years. So, in 2007, the first team in that year, they dropped the Rubin square error by 8%. In the second year, they dropped the error by 9%, and in the third year, finally, we have a winner. And the winner's approach blended over 800 different models. And Netflix said that they never really use the winner's approach, perhaps because it's too complex. Or perhaps after 3 years, perhaps correctly predicting users' taste, perhaps not their first priority. As I said, after 3 years, perhaps they move on to streaming services. Accurately predicting a user's taste, perhaps not that important after 3 years. So anyhow, they said that they never really use the winner's approach. But anyhow, because of this competition, we still learned a lot from all these methodologies. And I remember that in perhaps 2008, a lot of research papers, they said that I use Netflix data set and we improved the Rubin square error by how much percent, and that's a paper. They describe their methodology, that's a paper. And even Geoffrey Hinton, I said the one of the 3 Turing Award laureate in a couple of years ago. He published a couple of papers using this data set. So anyhow, because of Netflix price, we found that factorization-based approach is a good approach to predict users' taste on the items. We will introduce this later. And we also discovered that implicit features, temporal effect, and neighboring effect are useful features. Again, I will tell you more about this later. And regularization is important in this task. Regularization, if you remember, is the technique to prevent overfitting. And it's very important for this particular task. Okay, so we will discover some of these topics in the following, this week and next week. Okay, so we will introduce some of the recommender system techniques. So for recommender systems, we could roughly divide the techniques into 2 types. One is content-based, one is called collaborative filtering. For content-based, it's basically based on, for example, this user's characteristics and the movie's characteristics to make recommendations. So for example, based on perhaps experts' knowledge, they might say that males tend to prefer certain kinds of movies. Females may tend to prefer certain kind of movies. That's probably one thing. Or perhaps kids tend to prefer certain kinds of movies. Adults tend to prefer another kind of movies. So based on this attribute, you might be able to define some rules. That's what I call by content-based methods. You may have some characteristic of the movies, you may have some characteristic of the users, and then you make recommendations based on these attributes. On the other hand, the collaborative filtering, they don't rely on this characteristic at all. They just want to use people's previous ratings to predict their future ratings. That's the only clue. So let's first talk about content-based. So you may have users' profiles, their interests, their genders, and so on. And you might also have item information like movie's title, the actors and actresses, directors, content description, and so on. And you could compare the similarities and to make predictions. So the disadvantage is that sometimes the user information and item information may not be available. So for example, you might not know whether this user is a male or female. You might not know his age. You might not know his background. Likewise, for the items, in certain cases, item description may not always be available. For example, for movies, you might have this kind of title, genre, actor, actress, this kind of information. But if we change to another field, for example, like you want to know whether people will like certain music or not, then you need to have different kinds of music information. If we shift to, let's say, books, perhaps you need to have another kind of information. Right? So for different kind of items, you may need to have different kinds of information which is not always available. So there's a disadvantage of this kind of methods. And for collaborative filtering, you only need to know users' previous ratings on items. You don't need to know users' information at all. You don't need to know items information at all. You just need to know users' previous ratings on items. So it turns out that CF, or collaborative filtering, it turned out to be a very successful type of recommendation methodology. And in the year of 2000, Amazon has already published a paper telling people that they use this kind of approach and turned out to be very successful for their book recommendation. So we will introduce some of the most successful CF methodology later. So cross-domain, because we don't need to collect different kind of information for different kind of items. And we don't need to have the content information. And there are several different types of CF methods, which we will introduce all these methodologies. Okay, so what's the mass form of collaborative filtering? We only have some users and items and users' ratings on some of the items. And we want to predict these question marks. Okay, so this is the math form. Given some ratings and you want to predict the unknown ratings. So this is exactly the setting of Netflix price. And if I ask you how to make the prediction, what will you do? So let me pause for 5 seconds. If you think about it, if I give you this problem, how can you solve it? So this setting looks a bit different from what we have introduced so far, right? So for most of the time we introduce supervised learning. So for supervised learning, we need to have features and targets as a training data and test data. So here the target is obvious. That's you want to predict these ratings. That's a target. But where are the features? It seems that there's no features here. So at least for the first look, it seems hard to apply supervised learning methodologies here because there seems no features. We only have the targets. So how to do that? So it turns out that after some modeling, we can leverage the techniques we have learned to solve this problem. So the first one I want to introduce is called user-based collaborative filtering. So the idea is that how to recommend items for a user. Okay. So let me tell you the key idea here, and I will give you an example. The key idea here is that I want to predict or I want to identify which set of users are similar to user U. If I can find the users that are similar to user U, then I will check which items. Let's say if user V is very similar to user U for some reason, and if user V give very high score to certain movies, then perhaps user U will also like those movies. That's a key idea. So how to find the users that are similar to user U? So let's use this example. We have 5 users, Anne, Bob, Chloe, Dave, and Ellie. And we have 4 movies, movie 1, 2, 3, 4. So in general, most of these entries will be question mark. But for explanation purposes, I only have 1 question mark here. So the first step is I need to compute the average score of these users based on the available ratings here. Okay, so that's average score. And the next thing is I need to compute which users are similar to user Dave. And to do that, I just compute the cosine similarity based on the ratings, based on the available ratings. So cosine similarity between Anne and Dave. Let's use Anne and Dave as an example. So the intersection is this 3 and this 3. This one is unknown, so I just ignore movie 2. Okay. So the cosine similarity between Anne and Bob is based on this 333 and this 310, these 2 vectors. So the cosine similarity is 0.73. Likewise, I can compute the cosine similarity between Bob and Dave, Chloe and Dave, and Ellie and Dave. It turns out that Bob and Ellie are similar to Dave. So to predict Dave's score on movie 2, I will use Bob's score on movie 2 and Ellie's score on movie 2 as a reference. So my prediction is like this. On average, Dave gives 1.33 to a movie. So I use 1.33 here. That's the average score Dave will give to a movie. And then let's check Bob and Ellie. On average, Bob gives 2.75, but Bob gives 4 to movie 2, which means that Bob believes movie 2 is a good movie. By how much? By this much, 4 subtract 2.75. And likewise for Ellie, on average, Ellie gives 1.25. But Ellie gives 2 for movie 2, which means Ellie also believes that movie 2 is better than average. By how much? By this much. Okay? So I just use a weighted sum of these 2. And what are the weights? The weights are 0.88 and 0.85, which is their similarity score to Dave. So this is my predicted result. Okay, based on this Bob and Ellie, we believe that movie 2 should be better than average for Dave by this much. And Dave's average score is 1.33, and he believed that, and we believe that Dave will give a high score to M2 by this much. So this is our prediction. So after all the discussion, do you feel like this methodology is similar to what kind of methodology we introduced in this course? It's actually very close to Canyon-Snaber's algorithm. Essentially, we just use M1, M3, and M4 as the features. So we use M1, M3, M4 as the features. We try to find which users are close to Dave. Right? KNN, we use features to decide which axes are similar to the target X. Right? So we found that Dave and Bob and Ellie are close to Dave. So we use Bob and Ellie's prediction on M2 as the hint to predict Dave's rating on M2. So that's almost like KNN. Right? We find the k-nearest neighbors and we use their Y's to make prediction. Okay, so I'll stop here. And let's continue to discuss this next week.